So in this video, we're going to look at translating from our rectangular form for complex numbers to polar form. So currently how we would describe the position of this complex number on the Argand diagram is we would say go across 2 on the real axis and go down 2 on the imaginary. This isn't the only way that we can describe the location of this point on the Argand diagram. We can also talk about it in terms of rotations, and that's where polar form comes in. So polar form has the general format or cos theta plus I sine theta. And what each of these pieces are is they are the modulus or, and our argument is what we call the angle. So our angle, and we're going to see exactly what angle we're talking about now. So the modulus is called or because it talks about the radius of the circle that we're about to draw. So the modulus is the distance from the origin to our coordinate point, our complex number on the Argand diagram here. And what we're going to do is we're going to imagine that point being on the end of a string, and then we're going to imagine that if we were to draw that around, it makes a circle and it comes back around here. So that's why we call the modulus or. If you see that again, what we have is we've got our point on a string and we were swinging that around. We actually create a circle with that radius length there. So that's our or, our modulus. And our angle is actually imagining if we had our value here, so we had our radius here, and if I actually picked that up and I swung it around, how many degrees have I rotated around? Where would that point be? So that's what we're talking about there. The angle of rotation around anti-clockwise, that's our theta. Now in this question here, we're actually dealing with a theta that goes around, and it's not quite at 360 degrees here, it's just before it. So we need to figure that out by using a reference angle first. So I'll need to figure out not theta first, but a reference angle first. So this is what I need to figure out about the complex number. I need to figure out the value of or, and I need to figure out that reference angle there. And what I can see is that actually this makes a triangle here. So if I was to draw down, I've got a distance of 2 in this direction going across here. So if I draw out to that blue line, I've got a distance of 2 across there, and I'm looking for or. So if I redraw out that triangle for myself, I'm looking for or, which is this distance here. I don't know what that is, but I do know I have another distance going up this way. Let's just draw it up here. That's going to be 2, and our red line to the blue point is also going to be 2. And because they are perpendicular, I can mark that in as a right angle. And what I can see is that or is actually going to be quite easy to find. It's going to be Pythagoras' theorem. So I can say that or squared is equal to 2 squared plus 2 squared. So 2 squared plus 2 squared. And to get what or is on its own, I would need to say that or is equal to the square root of 2 squared plus 2 squared. So 2 squared actually works out to be 4, and this other one also works out to be plus 4. So we've got or then is equal to the square root of 8, which we could also write out as it's equal to 2 root 2. So just using surds, I can write or as 2 root 2. Now the other thing I needed to find was the angle, the reference angle. So what I need to do with that then is, well, I can use trigonometry here. I've got a right angle triangle, I have a missing angle. I know the opposite and I know the adjacent. So I actually have tan of that angle. And I know that tan of that angle is equal to opposite, which is 2. So the blue 2 is going to be our opposite over adjacent, which is going to be all over the other 2. And to get what the angle is on its own, I am actually going to have to get rid of that tan, and I do that by getting tan inverse of the other side. So I'm going to get tan inverse of 2 over 2 then. And if we put that into our calculator, being careful to close our brackets and follow all of the rules of trigonometry when we input it, you should get out that your angle, your reference angle inside there, is 45 degrees. So that's what we're looking at. I've now found out what the reference angle is. So not theta yet, not the angle of rotation we're talking about, but I have found a reference angle which will help us. And I'm going to be able to use this value here, which is the radius of that rotation, that circle around, which is the modulus. So I found that, the modulus, and I now need to work out the argument theta, which is the angle going right around anti-clockwise from the real axis. So what I can actually see is that that almost goes 360 degrees. So if I had my line here and my point was on the end of that string, I'm going right around almost to 360, but I actually stop right before 360. And what I have stopped by, I've gone back 45 degrees. So what I'm going to say now is that theta is actually equal to the 360, which I almost do, the 360 almost the full way around, take away my reference angle because I haven't quite reached the 360, so take away 45 degrees, and then I'm going to be saying that theta is equal to 360 minus 45, so I get 315. That's going to be my angle, my argument that we're talking about here. So that's what I needed to find, so I've also got that. And then what we can do is we sub it in to the formula, which was, again, it was going to be r multiplied by cos of theta. So r multiplied by cos of theta plus I multiplied by sine of theta. That's what we have. And now we just fill those in for ourselves. So we're going to say r was 2 root 2. So we say 2 root 2. Cos of theta is going to be cos of 315 now. So I'm going to put in 315. So cos of 315 plus I sine of 315. So I sine of 315. So I fill that information in and I close my brackets. And what we said was that if we wanted to check our answer at this stage, what I could do is I could actually multiply this out and I could say, okay, I have 2 root 2 cos of 315. So 2 root 2 cos of 315. And I have 2 root 2 I sine. So 2 root 2 I sine of 315. And if we put that into our calculator, if I went to my calculator and I said 2 root 2 multiplied by cos of 315, I should get out my 2 from the beginning. And if I put in I sine of 315 multiplied by 2 root 2, I should get minus 2 multiplied by I at the end. Like that, so 2 minus 2i. So I get back out the rectangular coordinates because again, this isn't changing the value of the coordinate or the location of the point in space. It's just finding another way to describe it, and it's describing it now using rotations.